Hi, my name is Bill Dally. I'm Chief Scientist and Senior Vice President of Research here at NVIDIA Corporation. And I'm going to share with you today some insights from NVIDIA Research. I think I have the best job in the world because I get to work with a lot of really talented researchers that make up our research organization. They're loosely organized into a supply side of research. And this part of research supplies the technology that makes GPUs better, from circuits, VLSI design methods, architecture, networks, programming systems, and storage systems. And the demand side of NVIDIA Research, which drives the demand for GPUs by developing new and better applications that basically use GPUs to solve important problems for human beings. Occasionally, we'll actually take some people out of multiple groups and have an integration or a moonshot group. We did this at one point in time to do a research GPU that later morphed into Volta. And we did this to develop what we called our tree traversal unit, which turned into the RT cores in Turing. Overall, we've got a great bunch of people solving a lot of really important problems. And I wish I could tell you about everything they're doing. I'm going to have to select a few things today. Before going into the selection for today, though, let me talk about a few things. First is the reason we do this research is to have NVIDIA products be better and to have uses of GPUs be more powerful. And so over the years, we've gotten what we call some of our greatest hits. Almost all of the ray tracing work at NVIDIA originated at NVIDIA Research. We started off developing, the original software ray tracer, which became the optics product. And then later on, we developed the TTU, the tree traversal unit that traverses bounding volume hierarchies and does ray triangle intersections. That basically made real-time ray tracing possible and is a core of the RTX feature in the GeForce chips today. We started the first networking at NVIDIA, developing NVLink and NVSwitch prototypes with NV Research, and that's now turned into a way of scaling up our GPUs into larger clusters that work very effectively together. And the very first neural networking at NVIDIA was done, developing a system that replicated the finding cats on the internet neural network with collaboration with Andrew Ng at Stanford. And the software that came out of that turned into cuDNN and really kind of led our whole charge into neural networks over the years. We've done a lot of things since then: RTX DI, RTX GI, DLSS. A lot of the core things in our current graphics offerings came out of NV Research. We're still doing great stuff in GPU architecture and in networking. And we're driving the state of the art in things like generative networks with our StyleGAN and its predecessors. But I don't have time to talk to you about those all today, so I'm going to pick a subset. This is the third of these insights from NVIDIA Research that I'm giving you. So I'll remind you of some of the previous ones, and I'm sure you can go back and find the recordings if you're interested in these. So in spring of 2021, I talked about our efforts in DWDM photonics and how we're really trying to revolutionize how we signal over reasonable distances between GPUs and switches. I talked about our efforts in deep learning accelerators with our magnet accelerator that was achieving 25 teraops per watt. I will report an update in that we, at the VLSI Circuit Symposium this year, reported on magnetic BERT, which is a new version of this deep learning accelerator that's 96 teraops per watt. So we currently have the most efficient deep learning accelerators on the planet. And a really cool thing that we showed back in March of 21 was GANcraft, where we can take a Minecraft world and turn it into photorealistic images. And then this past March, I gave an update on our autonomous vehicle research, how we're applying AI to design better chips so that we can then have better AI to design even better chips. How we're building GPU storage systems with fine-grained direct access from the GPUs to large tables without having to get the CPU involved, and how we're applying AI to science with our Fourier neural operators and their application to ForecastNet, which basically does weather prediction much faster than it is able to do with traditional numerical weather models. So today what I'm going to do is talk about four different things. I'm going to start at the low level and work up to the top with how we're going to signal between multiple chiplets in the future, and then a way of greatly increasing our memory bandwidth and reducing the memory energy. I'll talk about instant neural graphics, which is a really cool twist on the NeRF technology, which a lot of people have been using to great effect. And I'll talk about how to personalize image language models. So let's start with the chiplet signaling. You can imagine a future future system may look like this, where we have a number of GPUs that are on a silicon interposer. Those silicon interposers we connect up within them with an ultra short reach link. This is going a couple millimeters in a relatively benign, largely resistive channel. We then plop these down on an organic package, and we have a little bit longer links that connect those. One application of this is in future systems, we will have our network switches connected on interposer with our DWDM technology that I talked about in March 2021, this electrical optical interface here. And that connection between them is the ultra short reach link. At the other end of some of these links, we're going to have our GPUs connected to each other with ultra short reach links and to the EO, the basically co-packaged optics with the same links. To drive the demand for what the spec is, for what we have to achieve with these ultra short reach links, we can look at this presentation from the ISSCC forum in 2021 that we need 800 terabits per second coming off of one of these switches. And with a switch chip of 25 by 32 millimeters and using 90% of the periphery for that, we get this need of driving 15.1 terabits per second per millimeter. That's a bandwidth density we need around this perimeter to be able to match what we see as being switch demand in 2030. So if we had a 50 micron bump pitch, which is what we're facing right about now, we would need 70 gigabits per second to do that. But we anticipate scaling to a 40 micron bump pitch in this time frame. So the real requirement is to have each of these signal lines, and these are single lines, not differential. We double the requirement if it was differential. Each of these single-ended lines operating at 50 gigabits per second. So we need to be operating at 50 gigabits per second per pin, up to 1.2 millimeters on a silicon interposer channel. It's got to be a very compact design so we don't chew up very much die area, because we don't want to put a very big tax on breaking our design up into chiplets. And we want to make this to be a very low power design. And our approach to making it low power is to build the simplest circuit we can possibly build, which is a CMOS inverter. How are we going to do that? Well, we looked first at what modulation scheme we might use for this. And there are a bunch of different tries. The straightforward way of doing this is to use what's called non-return to zero signaling, basically just signals zeros and ones across the line. It's simple. We can forward the clock. It has excellent data and clock tracking because their data and the clock are both swinging the same amount. But we basically have to signal at a pretty high rate to hit this. We would have to be at 50 gigabits per second NRZ to hit our 50 gigabits per line thing. It's got higher loss or small timing margin, high power to be operating at that 50 gigabits. Another approach would be to basically drop to 25 gigabaud by running 50 gigabits PAM4. So now our data I is doubled in size from 20 picoseconds to 40 picoseconds. Being able to drop the Nyquist frequency down to 12.5 gigahertz is a huge win. But the problem is, by sending things as PAM4 with 4 different levels here to send 2 bits in every symbol, 2 bits per baud, we need a linear channel. So we need a linear amplifier. And the data and the clock don't track well because the data can be making transitions of 3 different sizes and the clock transitions are all the same size. This also gives us some inherent ISI. So the system we wound up settling on is this bottom one here, where we're going to operate at the same 25 gigabaud, but we're going to basically do NRZ in both directions simultaneously, what we call SBD, simultaneous bidirectional. So here we see that we have the TX plus RX summing together in this eye to give us multiple levels, but what we're sending in any one direction is really just a binary signal. So this has all the advantages of NRZ with the advantage of the half signal rate of the 4PAM. We get a wide timing margin because we now have 40 picosecond eyes instead of 20 picosecond eyes. The data and clock transitions are of the same magnitude, so we get excellent data clock tracking. And the only real issue we have here is that it's sensitive to reflections. If we get an echo, it doesn't get canceled properly. We have high near-end crosstalk. Basically, what we're putting on the line, we have to subtract off, and we need to do that accurately. And we get this bidirectional interaction. But we can solve all of those through careful channel design. And so it's really an ideal signaling thing. And here's sort of a little cartoon on how it works. So first of all, suppose I'm sending the green signal from data A over to the B side and the blue signal from the B side over to the A side. On the wire itself, these 2 signals will add together. So what I see at the pad of A is a slightly delayed version of B added to A. And what I see at B is a slightly delayed version of A added to B at the B pad. So what I need to do at each side then is to do a subtraction. So what I'll do is I'll basically take the inverse of what I was transmitting here. This is A out, that's A out B for A out bar, A out inverse. And similarly on the other side, I'll take the inverse of what I'm transmitting and I'll subtract it out So what I wind up with is basically the signal that I was sending. And so what I get on the A side is what was being sent from B, and what I get on the B side is what was sent from A. So the challenge then becomes, how do I basically do this subtraction? I actually wrote a paper about this over 30 years ago, back in 1990, with two of my graduate students at MIT. And we actually used a differential amplifier. This is problematic because that amplifier is power hungry, expensive, and difficult to make completely linear. And because we have an active element here, the dummy here actually has to dummy up the whole characteristics of the drive as well as the amplifier. So it becomes very difficult to get an exact replica. Other people have done approaches where they use transconductance, GM here. But the problematic thing here is you need to invert one of these transconductance things, and it's hard to do that and match the delays well. So that approach doesn't work very well either. It turns out that the right way to do this is incredibly simple. It's simply to use a resistive passive network to do the subtraction. This does require that we have an inverse of our transmitted signal. So we have D and A here, and we have its inverse as well. We actually have the inverse feeding the transmitter because it's an inverting transmitter. And then we have the scaled version, 1/8 size, that's also inverted. We need a dummy RC network to kind of match the characteristics of the line, but we can get by with an RC and not have to match the dummy drive because it's entirely a passive network. And then it takes this sort of passive network of resistors to do the subtraction. Now, it turns out we can take these three resistors, which is what you would calculate to do the subtraction, and come up with an equivalent network for them, which is just two resistors. We feed that then into an inverter with a feedback resistor around it. You can think of this as being like an op amp with a feedback resistor and its negative input, or rather its positive input, tied to the inverter threshold voltage. And this winds up giving an extremely simple solution that works really effectively. And we then add some trim devices to match the impedance of these, both the driver and the replica, to the line. And we have a working system. So let's look at the whole system, where we'll have 16 lanes of data going in one direction, 16 lanes coming back the other way. So we start with the transmitter. We have a serializer where we have a half baud rate clock. So this is a sort of a 12.5 gigahertz clock coming in here that basically takes our 16-bit wide data and serializes it down to a single bit at 25 gigabits per second. It then goes into a pre-driver that generates true and complement versions of the data that are delay matched. We have some trims in here, so we can basically go through a calibration procedure to exactly match the delay of the main data and its inverted replica. The final driver drives the line with the appropriate signal level and a matched impedance into the line. And then we use that resistive hybrid to basically subtract out our transmitted replica. And this inverter with the feedback resistor acts as a transimpedance amplifier to generate the received signal only, subtracting the transmitted signal off. The signal at this point then gets delayed to match. There's basically a delay adjustment here to match things. All the data on the clocks wind up lining up and gets deserialized with a half-rate receive clock that comes in here. The clock forwarding is done by taking one of these lanes and making it a clock forwarding lane. And that lane basically feeds the clock directly through, and it clocks all of the receive elements. So this basically shows how the clock forwarding architecture works. We basically are sending the transmit clock from the A side here, which has a PLL which feeds into the serializer. The serializer is set to send a repeating alternating 0 and 1 pattern for the clock. That's AAA in hexadecimal. And on the receiving side, we basically receive that clock. We don't really have anything to subtract off from it, so we basically leave a fixed input there. And we have a variable delay, and we use that then to clock all of the deserializers on the receiving side. The overall physical layer then works in a similar direction, coming in the other direction. We feed the clock back sending AAA on this signal and use it to clock our deserializer on the other end. So you can see these clocks walking through the lines and clocking on either end. And by running through a training procedure to set these delays, we can center these clocks in the middle of the eye and get very good recovery of the data on the data lanes. And the really key thing here is we're using exactly the same circuit to send the data and send the clock. So everything winds up saying matched over variations in temperature and voltage. So to test this out, we built a small test site on a 5-nanometer production part. We built these big GPUs and switches, and very often we can find little pieces of silicon area that aren't completely used. And in this case, we used one piece of that silicon area to build 2 of these 16-lane PHYs. We actually only connected up 20 lines here, 10 lines here and 10 lines there, and ran this under a 0.75 volt supply voltage over 1.2 millimeters of channel. This is basically a channel on a chip, but we basically designed the channel to exactly match the characteristics of an interposer channel, including the bumps. And if we look inside of one of these, you'll see that we have all of the transmit receive PHYs, some common clock logic, and the like. This is the bathtub curves, and what you see here is that at 10 to the minus 12th error rate, we've got an eye opening of almost 0.6 UI, and if you extrapolate that down, you wind up basically getting on the order of 0.45 UI at 1e minus 25. So the error rate here is extremely low. We have an extremely high timing margin, and the receive jitter here is under a picosecond. Where does the power in this thing go? Well, most of it actually goes to driving the line, the SPD FE. There's 15% in the deserializer and the serializer each, and the common clock logic is a little under 15%. The transmit and receive clocks are in the 5% range. Overall, we're under 0.3 picojoules per bit, and we wind up looking very good compared to various competition. If you look at other approaches to very short reach signaling, the real figures of merit here are in the bottom 2 lines. With a 40 micron bump pitch, we hit our 15.1 terabits per second per millimeter. That's better than any of these alternatives. In fact, compared to most of these alternatives, it's order of magnitude better. And similarly, our silicon density, we're at 21.6 terabits per second per square millimeter for the PHY area. That's 2x better than the nearest competition and orders of magnitude better than almost everything else. Here's some comparison to previously published works in the VLSI Circuit Symposium and JSSC. And again, we wind up being much lower energy for anything that's even comparable with data rate. We're actually much higher data rate than any of these things, and much lower power even than the lower data rate ones. And the only thing that we were comparable on power to doesn't really include the clocking power, so it's not really a fair comparison. Just to wrap up, we basically have demonstrated a simultaneous bidirectional channel where we basically can send signals both directions at the same time over a full duplex channel. We implemented a prototype of this in a 5-nanometer test site on a production NVIDIA chip. We've characterized this. It's under 300 femtojoules per bit, operating at 50 gigabits per second. And with the 55 micron bump pitch, it's 11 terabits per second per millimeter. It will be 15 once we drop the bump pitch to 40. And this is over a 1.2 millimeter channel. So I'm really excited about this technology because as we go forward, we're going to be building our systems out of many chiplets combined on interposers. And it's really critical that we have the ability to get very high bandwidth between these chiplets at very low energy and a very low area tax core chip to basically reduce the overhead of us breaking the chips up into multiple chiplets. So let me switch gears and talk about a different type of signaling and a different bandwidth problem we have. If you look at our history of our GPUs, going from our Fermi generation back in 2010 to our Hopper generation, the gap between our floating point performance and our memory bandwidth has been greatly increasing. So over this period of time, our double precision floating point performance has increased by 80 times. But at the same time, our memory bandwidth, as high as it is in Hopper, has only increased by 17 times. And so we've gone from a byte per flop ratio of 0.24 in Fermi to 0.03 in Hopper. And this winds up being challenging for many applications because a lot of applications need a higher byte per flop ratio. So there's some, Hopper is 0.03. It's going to be way down here somewhere on the left side. There's some applications that are very compute intensive, and they can get by doing. Let me go back here and say what this means is that we have to do 30 floating point operations, 33 actually, for every byte we fetch from memory, or we wind up being memory limited. There are some applications that are completely compute intensive and will do that. But most applications require more than 0.03, put the 0.03 line over here somewhere. And some of them require even more than 1 byte per flop. They're very memory intensive. So all of these applications can't really use the huge floating point power of our modern GPUs. They're memory system limited. They're limited by this limited memory bandwidth. Why do we have this memory bandwidth problem? And it's because if you look at the way we package our chips in the memory, we put the memory, here's a GPU SXM module. The GPU is in the middle here. We have these 6 stacks of HBM memory. They're on the outside of the GPU. So all this memory bandwidth has to cross the perimeter of this GPU. And we're very much limited by the figure of merit of terabits per second per millimeter on how much bandwidth we can get in and out of this. We also wind up moving these bits sideways a lot. They've got to move from way over here on this memory chip over to the edge of the memory chip, typically over to the middle of the GPU and then out to the requesting SM. So we're doing a lot of lateral movement, typically many centimeters worth of lateral movement. And that actually drives, the HBM itself is 5 picojoules per bit. There's probably close to another 5 picojoules per bit for data movement after you get it off the HBM and onto the GPU. So the sideways data movement is really the expensive part of the DRAM access, actually accessing the mat itself in the DRAM bank is probably on the order of 0.1 picojoule per bit. The other 4.9 is data movement sideways. And at this 5 picojoules per bit and the 3 terabytes per second we have in a Hopper GPU, we're running 120 watts just in DRAM power. So it's problematic for us to scale our DRAM power unless we can somehow reduce the energy per DRAM access. So the concept we're playing with here now is to stack the GPU directly, to stack the DRAM directly on top of the GPU. And this has a lot of nice properties, but let me tell you a little bit how we got here. It's really combining a bunch of things that have been going on for a while. So for many years, there have been stacked DRAMs. There's a product called HMC where the DRAM was stacked on a base layer that then signaled with high-speed PHYs. Our GPUs today use HBM memory where we stack the DRAM on an interposer next to the GPU. We combine these ideas of stacking DRAM with some ideas we previously published back in 2017 to build what we call a finer grain DRAM, which is rather than treating the entire DRAM die as one big unit that you would talk to, we would basically break it up into a bunch of sub-die that are essentially completely independent and have their own channels back to the GPU. And this basically was much more energy efficient, gave you much higher bandwidth by being able to talk to smaller units independently. We combine these, we can basically take the fine-grained DRAM, stack it directly on top of the GPU, and directly over each SM on the GPU is a small independent unit of DRAM that doesn't need to communicate with anything else on the DRAM die. This has a lot of nice properties. The first is because we're using the area of the DRAM rather than its parameter for signaling, we can get an order of magnitude more bandwidth, 10 times as many bits per second from the DRAM to the GPU. The other is because we don't need to move the data sideways. We can go from being 5 to 10 picojoules per bit, that extra 5 is adding the on GPU data movement, to on the order of a half a picojoule per bit because we're simply moving the data straight down. We basically have to access the array on the DRAM and then drop the bits right down to the GPU die. So we get much higher bandwidth, order of magnitude higher bandwidth, order of magnitude to factor 20 lower energy per bit. And so here's sort of a little bit of a cartoon of how it looks. On a GPU die, we simply have a bunch of SMs. There'll be a lot more than the 9 sort of shown here. And each SM will have with it a unit that maps its memory addresses to locations on this die and an interconnect that will either forward a memory request to the DRAM directly above this SM, if that's where the map indicates that the request needs to go, or over this on-chip network to whichever tile is what we call this basic unit of SM with its DRAM stacked on top. If it is going to the DRAM directly above, it goes up to this DRAM layer where the DRAM IO will receive that and then route it to a correct bank and channel, and then pull that back down. And so basically, the communication of the DRAM is up just a few tens of microns vertically, and then a small distance, less than a millimeter horizontally to get to the correct bank and access it. Here's sort of a larger scale view of that. You can think of each of these little tiles here, about 1 millimeter on a side, as being an SM with 100 gigaflops of double precision performance and 100 gigabytes per second of DRAM bandwidth. So over a typical GPU die, which may be 16 by 16 SM, say it's 16 millimeters on a side, much smaller than a GPU die today, we would have 25 double precision teraflops and 25 terabytes per second. You put 4 of these together, and you would wind up getting something close to modern GPU size that's 100 teraflops and 100 terabytes per second. With 48 gigabytes of DRAM capacity, over the 16 by 16 millimeter die. If we put a bunch of these stacks on a interposer of maximum size, we can wind up getting reasonably interesting sizes and capacities. But there are a bunch of challenges for us to make this work. We've been running a bunch of projects actually across a couple of different groups in NVIDIA Research to tackle these. Some of them have to do with packaging and signaling. Our current approach is looking at using hybrid bonding with a pitch of about 6 microns on the GPU and DRAM die. This winds up making the overhead of the DRAM die quite small. It's probably less than a 5% area overhead for the vertical interconnect that goes up through the layers. And we've developed some signaling schemes, particularly for this very short vertical interconnect, that wind up being extremely efficient. So the signaling energy of getting to and from the GPU to the DRAM will wind up being on the order of 100 femtojoules per bit. Then we have to look at power delivery and heat removal. The power delivery is from the bottom of this through a bunch of die bumps, and that has to then supply the power for the entire DRAM stack. Probably the bigger problem is we have an SM that can wind up being collectively over the entire GPU of hundreds of SMs, hundreds of watts of power that we have to dissipate through the DRAM stack. And so we've done a lot of thermal simulations with an SM basically being roughly 95 degrees C at the top of the SM will drop 10 to 25 degrees C through this DRAM stack. It turns out silicon is a really good conductor, and with hybrid bonding, we eliminate those air gaps that occur between the die with traditional solder bonding. But we do have to get through these big areas of DRAM, which are basically big areas of capacitor. And the capacitors have a lot of oxide in them, which is not nearly as good a conductor as the silicon. But even so, our thermal simulations seem to indicate that we're going to be well within the realm of what we can dissipate if we can keep our cold plate temperature in the 50 to 70 degrees C range. Probably one of the biggest challenges with this, but I think it's one that we're going to need to face reasonably soon anyway, is it introduces a non-uniform model of memory. The GPU memory model today within a single GPU is uniform. That is, every SM can access every frame buffer essentially with the same bandwidth and latency. It's not quite true. Our recent GPUs have been broken into what we call micro GPUs, and within each micro GPU, there is some locality, and you're better at accessing your micro GPU than something over in the other micro GPU. But this is going to take it to a much finer grain, and it's going to make it look much more like programming a multi-GPU system. Today, in a multi-GPU system, you can access all of one GPU's memory uniformly. But when you have to go to a different GPU, you do it via NVLink, and the memory bandwidth is reduced and the latency is increased. Here, that jump happens at the level of a single SM. That this SM can access its memory with very low latency, very low energy, very high bandwidth. We can actually build a network on chip so that over this entire GPU die, that the bandwidth can be uniform, but the energy cost and the latency goes up as we lose locality. And so we now have to understand how to deal with this non-uniform memory. If we can deal with the non-uniform memory, there are many ways of doing it. So the first is we're looking at some higher level programming models we have this programming model called Legion and Legate, and the Q numeric product is built on top of that. That can basically, it's a data-driven runtime, so it can reason about where data is located, do the placement, schedule the communication, make all of that work really well. And then for certain domains, for example, for deep, we simply have to take our deep learning frameworks and make them work really well with a non-uniform processor array. These will be stacked on top of, for example, our SPMD collective programming. A lot of people will program with Nickel or MPI or SHMEM. And those can be basically tailored to operate now, not just from GPU to GPU, but from tile to tile. We also can take our compiler technology, and by augmenting it with some low-level APIs, where we can, for example, now name locations where threads and data are placed and how large arrays are interleaved across these tiles, we can basically work to optimize the locality and maximize the parallelism for a lot of these applications. And we already have some data from some applications, things that are really completely memory bandwidth limited, like a Gauss-Seidel smoothing algorithm. It's a sparse linear algebra problem. We basically increase our bandwidth by 10x, we get 10x performance. And so there's some big gains to be had here for these memory limited apps. Also, quantum simulation is a comparable application. But there's a lot for us to do, I think, before, again, I have to caution you that this is entirely a research project. It does not represent anything that is planned on the horizon for NVIDIA to be offering as a product. And before we would get to that point, we have to solve a lot of these problems. On the packaging and signaling side, we really need to work out the optimal signaling to go up through these layers to talk to the DRAM. We need to understand how to distribute power through these layers and how to remove the heat. On architecture, we really need to work on maintaining enough memory level parallelism. If you have 10 times as much memory bandwidth, it means your SM needs to be able to launch 10 times as many memory operations to keep that memory bandwidth busy. And so we have to understand how to adapt our architecture to do that. We need to now have a very efficient DRAM controller to deal with this bandwidth, so that controller doesn't become a limiting factor. And we need to co-optimize how we're going to do error detection, both statically at configuration time, so we can assemble these GPUs and DRAMs and then configure known working parts, and at runtime, so we can work around errors that occur at runtime. Probably the biggest challenges are on the programming system side, because now we need to worry about non-uniform memory at the level of individual SMs, not just at the level of whole GPUs. And so first, like a doctor, we want to do no harm. We want to make sure that any program you have that runs well today will run well on this, at least will run no slower. You may not be able to use all of this great memory bandwidth, but it will not run any slower because it's now being run in this new memory system. Then we need to basically come up with mechanisms that allow us to control where the threads and where the data are placed in such a way that we can get the threads distributed so we get a lot of parallelism, but keep them close to the data they operate on so we get a lot of locality. And then we need to figure out how to make it very easy for programmers to do this with higher level programming systems that automate these details so you don't have to place each thread and each byte of data yourself. So let me move now from the supply side of NVIDIA Research to the demand side. I am very excited about our research on stacking DRAM on GPUs. I think it's going to wind up enabling a lot of demand side applications, which today are memory limited. This is true of both scientific applications, many of which have byte per flop ratios that are in the range of 1 to 4, way above the 0.03 that we're able to deliver with Hopper. And also things like ray tracing are actually memory bandwidth limited. So I think it's going to help our graphics side as well. Let me talk now about instant neural graphics. This is a really cool technology that we've developed recently, where if you have a scene like this, which you can capture with a couple dozen images in just seconds, we can then take these images and build a neural network that will let us do reconstruction in real time. And so with this reconstruction, because we're doing it with ray tracing, we can change, for example, the camera parameters, changing the depth of field and the field of view. And this is actually ray tracing individual rays that produce this image blur. We can focus at different points on the image, on that screen, on the block, on the robot arm. And it's basically calculating the actual image that you would see with these camera parameters. You can also extract the geometric features from this so that I can then feed them into downstream tasks. I can get the density distribution, the surface normal, the 3D position, or the depth. And they can feed various downstream tasks for a typical graphics pipeline. And all you need to train this model is to capture a video of static objects. In this case, the person is holding very still, and extract a couple dozen frames. And what's being visualized right now are the viewpoints of the frames that were used to create this reconstruction. And then once you have the reconstruction, computing on a single GPU is about a minute. So how do we make this work? What is the magic? In the past, building a nerf took many hours. So how do we do it in under a minute? And there are really sort of three pillars of this. The first is the input encoding. What we do is we combine neural networks with hashes. And we do this at a multi-resolution, so that if we give a certain point, we can use that to index into this hash structure in an extremely efficient way. Once we have that very efficient input encoding, we can then wind up using a much smaller neural network than what has traditionally been used. Because it's very small, we do a fully fused implementation so that we don't have to take the activations out to memory and then read them back in for each layer. And this makes our neural network much, much faster than it would be if we did it with the standard framework. And then we basically take this and do a very specific GPU implementation that takes 10 to 100 times fewer steps than if we did a tensor-based approach to training this neural network. So if we feed all of these together, the data structure basically learns a level of detail. We have different resolutions in our multi-resolution framework, and it simply learns this as we train the network. Here's an example. We take this little Lego toy, and from just a couple of photographs, we can get a 3D representation. And then we can have viewers that basically instantly reconstruct this in a few seconds from a lot of different angles. But that's not all that we really enable by neural graphics. We can basically take our neural graphics and we can use this to compress images. We can represent shapes in terms of signed distance functions. And we can use them inside a real-time rendering system where the neural network learns the lighting of the scene so fast that it can keep up with the animation. Here's an example of that. We're actually running a scene and training a nerf on that scene so that when you look at these shadows, you're seeing the rate at which the nerf is learning what the representation of those shadows are. So you'll see the branches resolve and the shadows resolve at the rate that the network is learning. You see how the shadows of those leaves will grow and refine as we pause and give the network some time to learn. This is also potentially the future of photography, so that in the future we can have 3D photographs that look real. You'll capture a scene from a couple angles. You'll spend a minute on a GPU, and you'll have all of the things like hair, realistic reflections off of difficult materials that are difficult to capture. And it all happens with essentially no effort. Take a few photos, run our software. This is also the right way to do digital twins. In this case, we basically captured this workspace with a phone camera and less than a minute of processing on a GeForce graphics card. And we wind up with a digital twin of this workspace that we can then put objects into and generate images from arbitrary angles and the like. So if you're interested in this, you can go to this GitHub page, get your own instant NGP software and try it out for yourself. So the neural graphics are really cool. I think NVIDIA is all about graphics and all about AI, and this is a project that really brings the two of them together by using AI to produce graphics by just taking a couple of photos to build the model. And then the really interesting questions come on how we can compose new scenes by taking nerfs that we've captured of different things, composing them together with different lighting models and different environments and make all of that work. So there's a lot of interesting work to be done down the road in the future. Another approach to images and AI is really typified by visual language models that have recently occurred. You can type a caption like 5 zebras grazing a green field and have it produce this image. And these work by training these networks on huge bunches of images where we basically take the image, run it through a text encoder, take the text and run it through a we take the image, run it through an image encoder, take the text, run it through a text encoder, and we make sure that those 2 points wind up basically in the same point in a high dimensional joint representation. But what we would like to do is put personal items into these joint image and text learning, so that, for example, you'd be able to search your photo catalog to find an image of you in a particular situation wearing a particular piece of clothing. Or you could search a video and ask, when is the elephant on this toy wagon? Or you could command a robot by saying, make coffee in my favorite mug. But it would need to know, what is your favorite mug? How do you encode that? Well, the way these models work is they've trained this text encoder so that if you take a sentence like a dinner table with, each of the words in the sentence winds up being an embedding vector, basically a multi-bit vector of a word embedding. The text encoder takes those embedding vectors for the sentence and basically gives a point in this latent space that represents a concept, a dinner table with. But if I want to add to that a new concept, say my own personal teapot, which happens to be painted in this bizarre fashion, I need to basically take an embedding vector for this teapot and make it land in the right space here. And in particular, I need to make a sentence, a dinner table with my teapot, land in the right space there. The traditional way to do this would be to have an adapter that you fine tune with your teapot image to get this point to be in the right place. The problem with that is that this adapter will mess up all of the things that you've spent literally, thousands of GPU months figuring out. You'll get your teapot in the right place, but everything else will move a little bit. So the adapters damage the representation of known concepts. So what we want to do instead is we want to invent a new word to represent our teapot and make sure that word maps to the right place. So we want it to handle a new concept with just a few images without messing up everything our network already knows. So what we're going to do is we're going to learn the embedding for this new word, my teapot, and we're going to learn it in such a way that it winds up in the right place. And the way we're going to do this is we'll go ahead and we'll basically take here we'll have images of a dog, and we'll take the image encoder. It will land it in the image latent space here. And then we'll take this set encoder to take those images, putting it in the word space so that this embedding vector for the word will land in the appropriate place. And the cycle loss is basically the distance between these 2 points in the image latent space and the text latent space. And that basically, minimizing that cycle loss, will tune this encoder to give us the proper embedding vector to put our new concept in the right place. Okay, so once we've done this, I can now, for example, use it for image search. So let's say I've trained a new embedding vector to be my skirt. I can say, standing with my skirt on a stone pathway, and it will find the image that best matches that and come up with it. And so we can see on a personalized image search, this winds up beating the other known techniques to do this. We can also generate images with this. So for example, if I learn this kind of bizarre sculpture here and give it a name, S star, I can say an oil painting of S star, and it will basically make an oil painting of that, or an app icon of S star, or Elmo sitting in the S star position, or crochet S star. It will take this concept and basically do different textures, do things in that shape, and do very well. Similarly, if I have this toy cat, I can call it S star. Sorry, and I can say a painting of 2 S star in a boat, an S star backpack, an S star lunchbox, and so on, and it will generate very accurately these things. And the way this works is by using a diffusion model, where we basically take an image and we add noise to it, this forward diffusion process, until it's essentially just all noise. But then we can do a denoising process going back to get an image, and we can train these diffusion models, both with the noising version and the denoising version, with our embedding token to land the image in the right place in the latent space. Again, using that loss model, and this is how we wind up being able to build a generator that can take a sentence, including a new word we've defined for our personal object, and make it work. So what does the model learn? In this case, let's look at 2 examples, a skull mug and a teapot. And I'm going to say, generate a photo of S. So S here is done by these 3 inputs for the skull mug and these 3 inputs for the teapot. And you see that it generates good photos of the teapot, And they're not, one-to-one, but they're pretty close to the teapot that we've given it. On the other hand, if I take some more traditional image generators like DALL-E, and I say, give me an image of a skull mug, and I can say a mug having many skulls at the bottom and a sculpture of a man at the top of it, which corresponds to this mug I have. The problem is that this sentence doesn't really capture this picture. And therefore, these images that DALL-E generates are kind of consistent with the sentence, but they're not what I wanted. I really need to take this picture and get its embedding vector to capture that concept. Similarly, a teapot with green, red, blue, yellow, an apple with leaves, and a lemon with leaves. Yeah, that's all on my teapot, but it doesn't look like that. It looks like this. And again, it's because this sentence doesn't really capture the picture. I need the picture to create the word of the picture, and then I can put that in the sentence. I can combine multiple concepts here. I can define, one of my novel words to be the clock and another one to be the style, and then basically ask for a photo of the clock in this style, a photo of the cat in this style, and so on. And I can use a new concept to control the style and shape. So I can say, a painting of this on a branch, or a house in a particular style, or a grainy photo of S-star in Angry Birds, an S-star made of chocolate. And so it basically takes this concept I have defined here as S-star and can apply it in a lot of different ways. So we can compare this to a lot of previous approaches. With time running a little bit short, I won't go into a lot of detail here, but I can take these input samples and basically see that with our approach, I get back out pretty much what I put in. I can take my clock and say, give me a photo of the clock. Give me a photo of the clock on the beach, on the moon, of Elmo holding it. And I get that. When I try to use any of these other models, I don't get what I want because I haven't been able to capture this concept of what my clock is. Similarly with the mug, if this is my mug, I can say a photo of my mug on the beach, on the moon, and Elmo holding it. And I get my mug. I don't get some other bizarre thing. And the reason I'm getting these bizarre things is I haven't been able to really capture the concept of what my mug is without training that embedding vector for my mug. So let me wrap up with just an overview of what I've talked about today. NVIDIA Research is really a wonderful place. It's like working in a toy factory. We get to play with lots of neat stuff that hopefully will have a huge impact on the future of GPUs and how they're used to make the world a better place. Today, I've given you, 4 little glimpses of that, 2 from the supply side, 2 from the demand side. On the supply side, I've talked about how in the future we're going to signal between multiple chips that we put down on an interposer. And to do this well, to meet what we see as the need for future bandwidth, we need to hit 15 terabits per second per millimeter along the edges of our chips to be able to meet the future bandwidth demand. The system I showed you does this by using simultaneous bidirectional signaling. We basically send signals in both directions on one wire at the same time. That essentially doubles our bandwidth at a single baud rate. So we get an effective 50 gigabits per second by sending 25 gigabits per second one way and 25 gigabits per second the other way on the same wire. Using a very clever passive resistive hybrid, we're able to do this at about 0.28 picojoules per bit, and with that density that's been better than any system that people have reported to date. The next problem I talked about is how we basically meet the demand for bandwidth in future GPU-based systems. As we've scaled our systems from Fermi to Ampere, from Fermi to Hopper, we've increased our double precision floating point performance by 80x, but our bandwidth by only 17x. So that we have this gap now. We used to have 0.24 bytes per flop of bandwidth. We now have 0.03 bytes per flop of bandwidth. And so for a lot of applications, we wind up being bandwidth limited. The concept we're experimenting with is stacking the DRAM directly on top of the GPU, which gives us 10 times the bandwidth and actually probably closer to 20 times the efficiency if we count both the energy of reading the HBM and the energy of moving that data around on the GPU chip. And that efficiency comes by eliminating the sideways data movement, across the DRAM chip to the edge of the chip, from the DRAM to the GPU, and then across the GPU chip from its edge to where that data is actually used. And so this actually has a number of advantages. The first one is for bandwidth limited applications, we can get 10 times as much bandwidth. But it also means that even for applications that aren't bandwidth limited, we wind up with 1/10 or 1/20th the energy for reading this DRAM. It also gives us the ability to continue scaling, even if we wanted to stay at 0.03 bytes per flop. We can continue scaling our arithmetic density now and be able to at least hold that that bandwidth ratio. The big challenge of this, I talked about a bunch of challenges in signaling and thermals and architecture, but the really big challenge here is it brings us a NUMA programming model. Again, we'll first do no harm. We'll make sure the existing programming models work well with it. You'll get the bandwidth advantage. You may not get the energy advantage, but to fully use the advantage of this, we now need to consider the location of the threads and the data on the GPU and try to line up the threads on a particular SM with the data that's stacked above this SM. And I think that is a soluble problem, but will require some innovations in how we program our GPUs. And I think that we'll be able to do this the way we usually do, through a bunch of very tuned libraries and also some high-level programming systems that can automate the task of mapping your threads and your data. And then I talked about two supply-side technologies. The first is instant NERF, which is a way of capturing neural radiance fields in seconds rather than hours. We can take a few dozen images in less than a minute on a single GeForce GPU, basically produce a neural network which now can render this image. We can basically ray trace with arbitrary camera parameters. We can change our field of view. We can extract the geometry. We can extract the surface normals. We can extract whatever we need to then re-render it in different lighting and the like. And the three pillars that make this work well are the real innovative one is the hash encoding, where we combine the neural network with a multi-resolution hash that basically really compresses what we need to know about the image to encode it. With this compressed form, we can then use very tiny neural networks to basically capture the NERF. And then with these tiny neural networks, we can do a very tailored GPU implementation to make this all blindingly fast. And then the final thing that I told you about was these personalized image language models, where we can take this very exciting field that's emerging of being able to couple text with image and go in either direction. We can either give a piece of text, use it to search a database of images to find what we're looking for, or to generate an image that corresponds to that text. Or we can look at an image and have it generate some text that describes the image. And what we'd like to do is to be able to take particular objects. If I have my mug, right, I'd like to get this mug in a particular image. I can, with a couple images of my mug, train an embedding vector to represent that mug that maps to the right place in the shared latent space between images and text. So now I can apply all of this power of coupled language image models to my personalized mug or my personalized dog or cat or whatever. It's really very, very powerful technique to couple these image and language models together. So this is just a tiny sample of what we're working on. I'll refer you to my previous two Insights talks on NVIDIA Research for a few other things. And I'm looking forward to probably next GTC giving you another glimpse. So thank you very much for your time and have a great day.